All right, so you're going to calculate standard error, and remember, S subscripted x bar equals S divided by the square root of n. All right, now we have a standard deviation of 1.35 divided by the square root of 150. So you guys go ahead and calculate that and tell me what that works out to be. What is our standard error here?
I got 0.11.
0.11, do you guys agree? Anyone? Marcus agrees, good. All right, so that was our first step, calculate standard error. Second step, what you're going to do is you're going to calculate the margin of error. M.O.E, margin of error. Sometimes I read it like Mo, like the Simpsons bartender, but you just remember it's margin of error, right? And Mo, now I'm going to say Mo, equals z squared some level of alpha times standard error. Right? Well, we know that the z-score that we're interested in is 1.96 because we want to build a 95% confidence interval. And our standard error was 0.11. So what does that calculate to be? To 3 digits. Go to 3 digits with this one.
0.216 if it's rounded up.
0.216. Do you guys agree? I hope so because I wrote it in pen. All right. The third thing you're going to do is you're going to use this margin of error and you're going to build, in this case, remember it's I'll put in parentheses here just to remind you guys, 95% confidence interval. We're going to build the 95% confidence interval. All right, which means you're going to have x bar plus and minus Mo. Right, which means that there's a lower bound of x bar minus Mo and an upper bound of x bar plus Mo. So our x bar, we had 4.6 arrests, minus our margin of error of 0.216, and the upper bound is 4.6, our mean, plus our margin of error of 0.216. Let me know when you guys get a lower and upper bound while I drink some more coffee. Does anyone have a lower bound?
4.384.
4.384.
And then for the upper bound, it's 4.816.
4.816. All right. So now from this point forward, I'll probably round this to the second digit, just so you guys know. And so a fourth thing I could do is draw the curve, just so you can visualize it. Which, of course, give it a title, which in this case is going to be a 95% confidence interval for property, crime, arrests per day. Right, you want to give it some kind of appropriate title. It's going to be centered on the mean, so 4.6. And the x-axis is going to get labeled as arrests. Right, that's what we're measuring. Right, draw my curve. My lower bound, I'll put it in. I'll round it now, 4.38. And my upper bound, 4.82. All right. So that's what, when I say I'm 95% confident that it's between these two values, right? That leads to a fifth thing that I could do. And oftentimes you'd be asked just to make a claim about the location of the population parameter. What's the true population value? Well, here's what we know. We would say something like this. We can be 95% confident that the average number of property crime arrests per day for all policing precincts in America is between 4.38 arrests per day and 4.82 arrests per day. Now the interesting thing is, you look at the statement here, and I'm actually not making a claim that the average is 4.6. I'm actually saying that the claim is that the true population value, I'm 95% certain, is between these 2 points. Right? And I think when you guys watch the news, or you watch the mass media, and they report out poll statistics or whatever else they're doing, and they talk about averages, and they talk about, the percent of people who, think Walz did better than Vance, or Vance did better than Walz, and I mentioned that because it was on last night. Whatever. They always report this. But the study is actually studying this. It's not studying this, it's studying this. It's saying, what's that range that I'm 95% certain that the true population value lives in, right? So if you ever hear a study done from a sample and they either fail to report margin of error or they just report this number with nothing else, you have no idea, right? They should always disclose sample size. They should always disclose margin of error, right? So, because then you can understand what the claim about certainty is, right? Which means, of course, that there's a 5% chance that it's either less than 4.38 or greater than 4.82, right? See if I can turn that on again. Yep, did it. All right. Now, a fifth and final thing I could ask you guys to do. Let's go back to the formula for margin of error. Mo equals Z times S subscripted X bar. But I could rewrite S subscripted X bar as equaling Z times S over the square root of N. You guys agree? Because this chunk of the formula here is just this. Right? You agree so far? Now, what happens commonly with a lot of research is you need, if you're a research professional, you need to cost out jobs. And to cost out jobs, the most important thing to tell a prospective client is how much it's going to cost them. And the thing that's going to determine cost more than anything is how much sample you gather, right? It makes a big difference whether we call 150 precincts or 2,000 precincts. Now, we're going to have a more accurate number with 2,000 precincts, of course, right? But it's going to cost a lot more money. In fact, when I was at the Ohio State University Center for Survey Research, we could cost out a job as essentially being the job is going to cost, there's a baseline, which we would often say is $20,000. And you think, well, what's that $20,000 for? Well, you've got to program the survey, you've got to train your interviewers, you've got to train your supervisors, etc. Right? You've got to do all the setup, regardless of whether you're contacting 100 precincts or 1,000. The setup is still the same, right? All right, and then we would charge plus maybe $30 per precinct we contact times N, the number of precincts that we would contact. So what we'd do is we'd take this margin of error formula and we would solve it So right now you can imagine mo equaling zs over the square root of n. And when you take this and you solve for n, what you're going to get is n equals z squared s squared, line there, over mo squared. And so if I use, for example, the previous standard deviation, I'd have to use some kind of standard deviation. I have to have a guess about s. Then I could figure out how much sample I would need. So let's say that the next year I'm talking to the National Association of Police Chiefs and they say, okay, we're going to use the previous standard deviation. So, okay, s equals 1.35. They tell you that they want to be within 0.1 of an arrest. They want to have more accuracy. They want mo to equal 0.1. 0.1. And they say that they want to be 99% confident, right? So instead of using 1.96 as the z-score, they now want you to use 2.575, right? So they're going to use the z-score for 99% confidence, 2.575. And then you would just take this formula, and it's a substitution problem, right? So you've got z of 2.575 squared times s squared, 1.35 squared, divided by mo squared, which is 0.1 squared. How much sample would you need to collect?
Is the first number 2.575?
Correct.
Okay.
Does that help? Getting closer won't solve my penmanship, but it'll give you a better look at it.
I think I have it.
What do you got?
I think they'd have to collect 1,208 and then 0.4314 samples. So 43.
All right. So here's and this is the correct answer. Here's an interesting thing though. Can you sample 0.43 of a precinct?
Mm-mm.
You have to sample the entire precinct, right? So here's the fourth rule of rounding, right? So you had 3 rules of rounding thus far, right? Proportions, percentages, and then generally. Here's the fourth rule. When calculating sample size, you always round up to the next closest whole number. You never round down. So the correct answer here is you need to contact 1,209 precincts. Right? And it doesn't matter what's after the decimal. If that's like 0, if it's 1208.00004, you still round it up. Because if you round it down, you're sacrificing either the agreed upon margin of error or how confident they were going to be, right? You'd be sacrificing one of these two things. They've said they want to be 99% confident within 0.1 of an arrest, right? So you always round that one up, the last one. Now, here's a fun fact for you as a bonus. So this would cost $20,000 plus 30 times 1209. And tell me what kind of a car we're shopping for. All right, Samira, you get a car. Marcus, you get a car.
Probably like a new BMW.
Why? What's the price? How much is it worth?
Hold up. Oh, I had the answer, but I'm calculating it on my iPhone calculator. It just went away. So
It's 56,217. So yeah, probably a BMW.
That sounds all right. Now, of course, you do have to pay your staff, just so you know. You do have to pay for your phone lines and your software licenses and all that kind of stuff. But this is basically, now I've used this formula, but like, for example, when I did the Stars and Stripes survey, this is how much I told the Smithsonian Magazine that I would need to do. I didn't come up with BMW numbers, but because I was doing internet, so I didn't charge $30 per sample. But when I did Charity and Security Networks, I was doing a phone survey, and so it was kind of closer to this number. So, I mean, this is how you cost the jobs out. And the people who do this, instead of wasting their life away as university professors, go into professional research. This is how they make their living, right? Super fun.